Understanding sklearn, Linear Model, SGD1Class-SVM. SGD1Class-SVM is a powerful outlier detection algorithm within the scikit-learn library. It's a variation of the classic support vector machine SVM algorithm tailored specifically for anomaly detection. Let's break down its core functionalities, key parameters, and how it operates. 1. The essence of one-class SVM. Traditional SVMs are primarily used for binary classification, separating data into two distinct classes. One-class SVM in contrast. One-class SVM focuses on identifying normal data points within a single class. It learns a boundary around the normal data distribution. Labeling anything outside this boundary is an anomaly. The one-class approach, the algorithm learns a decision function that defines a normal region in a feature space. Any data point falling outside this region is considered an outlier. 2. The role of stochastic gradient descent SGD. SGD, a workhorse for optimization. SGD is a powerful optimization algorithm commonly used to train machine learning models. It iteratively adjusts model parameters to minimize a loss function. SGD in one-class SVM. The one-class SVM leverages SGD to efficiently find the optimal boundary, defining the normal region. This makes it suitable for large datasets where traditional SVM optimization might be computationally expensive. 3. Key parameters and their significance. Penalty determines the type of regularization applied during training. L1 lasso encourages sparsity, forcing some feature weights to become zero. Useful when features are highly correlated, leading to a simpler model. L2 ridge shrinks feature weights, preventing overfitting and promoting stability. Generally preferred for most scenarios. Elastic net combines L1 and L2 penalties for a balance between sparsity and stability. Alpha, the regularization strength, controlling the penalty for model complexity. Higher values lead to stronger regularization and simpler models. Fit intercept determines whether to add a constant term bias to the decision function, often beneficial for better model fitting. Maxiter, maximum number of iterations for SGD optimization. Larger values allow more optimization but can be computationally expensive. Tolerance for convergence criteria. The algorithm stops when the improvement in the loss function falls below this threshold. Shuffle controls whether data is shuffled before each SGD epoch. Shuffling can improve training stability. Random state used for reproducibility. Setting a specific value ensures that the same random number generator is used for consistent results. Learning rate controls the step size during SGD optimization. Constant fixed learning rate for all iterations. Optimal adaptive learning rate that automatically adjusts over time. Scaling learning rate decreases inversely proportional to the number of iterations. Adaptive learning rate that adjusts based on the observed gradient. Eta 0 initial learning rate for the constant learning schedule. Powered exponent applied to the learning rate in the scaling schedule. Warm start specifies whether to reuse the previously trained model parameters as a starting point. For further training, can speed up training if similar data is used. 4. How SGD1Class-SVM works. Training. The algorithm receives a set of data points labeled as normal. It learns a decision function that defines a normal region in the feature space. This function is essentially a hyperplane in the high-dimensional space of features. The decision function is trained using SGD to minimize a loss function that penalizes points outside the normal region. Regularization is employed to prevent overfitting. Prediction. During prediction, Unseen data points are classified as normal or anomalous based on their distance from the learned decision function. Points inside the normal region are classified as normal, while those outside are considered outliers. 5. Use cases and advantages. Anomaly detection. Outlier detection is essential in various applications, such as fraud detection, network intrusion detection, and medical diagnosis. Robustness. SGD1-class-SVM is robust to noisy data and can handle datasets with complex distributions. Efficiency. SGD optimization makes it suitable for large datasets, enabling efficient training. Versatility. The algorithm can be used with different data types, including numerical and categorical features. 6. Limitations. Computational complexity. Training can be computationally expensive for very large datasets. Parameter tuning. Finding optimal hyperparameters like alpha, penalty, and learning rate requires experimentation and domain knowledge. Interpretability. The learned decision function might be difficult to interpret, making it challenging to understand why certain data points are classified as anomalies. Example usage with YAML configuration. YAML. Model. Name SGD1-class-SVM. Params. Penalty. L2 use L2 regularization for model stability. Alpha 0.1 set regularization strength. Learning rate. InVS scaling. Use inverse scaling learning rate schedule. Eta 0.01 initial learning rate for InVS scaling schedule. Maxiter 1000 maximum iterations for SGD optimization. Toll 1e-3 tolerance for convergence. Random state 42 set seed for reproducibility. This YAML configuration defines an SGD1-class-SVM model with L2 regularization, a specific learning rate schedule, and other parameters controlling training and optimization. Conclusion. SGD1-class-SVM is a powerful tool for outlier detection, offering efficiency and robustness. Understanding its key parameters and how it works enables you to effectively utilize it for various anomaly detection tasks. Always remember to experiment with different parameter settings to find the optimal configuration for your specific dataset and problem.